So when we're talking about growth and decay in a real life application, there's going to be a couple different equations that you could use. And it all depends on like how the growth is happening or how often the growth is happening. Yesterday, when we were discovering E, the gentleman who was in the video at first talked about getting interest once a year, and that gave you two pounds. But then as soon as you started getting interest monthly, so it happened 12 times, you got more interest. And then when we did it, weekly, we got more interest. That's what we're going to talk about today. Now, those more complicated situations had a more complicated formula. You started to see a formula that had like a 1 over an n with an exponent of an, it got a little bit more complicated. So the first formula that we're going to see here applies to a very basic situation where a real life amount of something, which is called a principal, increases by a fixed percent, r as a decimal, to the final amount, a, after t years. Okay, so essentially, this is our time. It is always in years, so that is important. So what if the word problem says, how much do you have after 6 months? What will this be? 0.5. Good. So yeah, you'll have to kind of make sure you're always being careful with that. Let me clarify what this means, r as a decimal, okay? What that really means is if I say 2.57%, sure, that has a decimal point in it. That's not what I mean by as a decimal. What I mean is as a portion out of 100. So if you were to write this out of as a portion out of 100, it would be 2.57 out of 100. And so then it becomes 0.0257. Everyone okay with that? You've seen that before. So we're converting, it's like saying 50%, you wouldn't plug in 50 into the problem, you'd plug in 0.5. It's a 0.5 chance of it happening. Okay, so that's gonna be important for that. The P is often called the principal, so just be aware in case the word, or the problem has that word principal in it, that that's like the initial amount. The only thing you have to be aware of here is that it could, if it was changing between growth or decay, the way that we would do that is with the plus versus the minus. So if it's a growth problem, the final amount is the initial amount times 1 plus the rate for that many years. And if it's decaying, then it's the principal times 1 minus the rate to the power of t. You have to know to do that. It will not be given as a negative percent. It will never be communicated as a negative percent. Okay, so you invest $200 in a savings account when you were 8 years old to save for college. The interest rate at your bank is 5.5% annually. So notice this says annually. So that's once a year. So if it's once a year, that's a very basic equation. How much will you have when you're 18 and ready to go to college? Okay, so this right here is my P. Let's see. If R is 5.5%, then what we really need to use in the formula is 5.5 divided by 100. So what we really need to use for R is 0.055. Okay, so that's what we'll use in the formula. And then if we started when we were 8 and now we are 18, how much time did we invest? 10 years. So our equation will end up looking like this. 200, 1 plus 0.055 to the power of 10. Very straightforward. Plug it into your calculator, hit enter, get your answer. So why don't we just try it, make sure we can put all those exponents in correctly. Okay, so 200 to the 1 plus 0.055 onto the power of 10. And we should get, what, 341.63. So, all right, you have all of $341 to go to college with. But hey, you started with 200 and added nothing. You got $141 for free. That's pretty good. So there it is. Now, suppose that the $200 is sitting in your sock drawer, not earning interest. Okay, so let's say you didn't put it in the bank. In 18 years, if the value of the dollar has decreased by 0.15%, what is the value of your $200 now? Okay, so this is this would be the argument that the bank would make for you giving them your money. They'd say, sure, you can put it in your sock drawer, but your $200 isn't going to be worth the same amount. So let's try this one out. The $200 is sitting in your sock drawer, not earning interest. In 18 years, although wait, wasn't it only 10 years in the previous problem? So let's make it consistent so that we can compare contrast. In 10 years, if the value of the dollar has decreased by 0.15%, which I think is a fairly realistic value, what is the value of your 200 now? Okay, so this is a depreciation problem. So we've got, we would have to use an R value of 0.15 divided by 100. So that would be 0.0015. So we would have $200 depreciating, so I'm depreciating it for 10 years. 200, so 1 minus 0.0015 to the power of 10. So your $200 can buy you $3 less than what it did, you know, which doesn't seem like a lot. But what if it was $1,000? Now it's a little bit more. Okay. So there's a value to putting it in the bank. 197.02. All right. There's occasionally you're going to see this word. Do you know what that means? To depreciate. It means like to lose value. Okay. If you buy a brand new car, you pay for it in cash. You drive it off the lot. The instant you drive it off the lot, it is worth less, which is kind of a drag. All right. Another term that you will see that you need to be aware of is this idea of compounded interest. We heard the gentleman talking about that yesterday. I've also talked about that. That's the idea of earning interest on your interest. So, you know, if you're compounding daily, the interest that I make today, when I go to calculate my interest tomorrow, I'm using the original amount plus the interest that I earned yesterday. So you're making money off of free money. Okay, so that's what that compounded word means. It's the interest amount paid on the initial investment, which is called the principal. And it's P-L-E, not PAL, like Mr. Silva, Principal. Okay. And it's so it's the interest paid on the principal and on the previously accrued interest. So just watch for that word compounded. That's going to be a more complicated formula. Although interest earned is expressed as an annual percent, the interest is usually compounded more often than once in a year. So therefore, our formula has to be altered. So here's our new formula. It is a little bit more complicated. Some of the letters still mean the same thing. In fact, all of them except for one. The P is the principal, or the initial amount. The A is sort of your final amount. The R value is always going to be your percent divided by 100. So it's your, percentage rate divided by 100. So it's always, as a decimal. And T is always your time in years. So that's important. Make sure that's always in years. And then lastly, this N value, which is the new part to this formula, that is the number of times we are compounding in a year. So number of times compounding in a year. And that is going to pop up twice in the formula. You will see it here, but it is also up here. Kennedy.
Will we get problems when it's not in years and we have to switch it?
Yeah, sometimes it'll be like you're investing this for 6 months.
So will we divide it and maybe that?
So then T would be 0.5 in that case. Or sometimes what it'll say is you are investing for 30 months. So then you have to go, oh gosh, 30 months, more than 1 year, less than 2 years. What's my proportion here? Oh, that's 1.5 years. Okay, so do remember that T will always be in years. Growth versus decay. The growth will have the 1 plus the R over N, whereas the decay will have the 1 minus the R over N. Okay, so you have to consciously know to choose the right one based off of the, the problem that's happening. Yes, sir.
So we only use this for compound interest when it's monthly?
Correct. So, what's that?
So you don't use it if it's annually?
Correct. So if it says once a year, you can use the more simple equation. I mean, you could use this one. Once a year would just have a 1 here and a 1 here. Which then turns it into the simple equation. So if it says annually, once a year, it's a more basic situation. The words you want to watch out for, he gave a good example. If it says compounded monthly, you would use N equals 12. What if it says compounded weekly? How many weeks are in a year? 52. You should probably memorize that. If you didn't know that. What if it says compounded biannually? How many times is that in a year? I think it's twice. What if it says compounded quarterly? That means it is happening 4 times in the year. And I think that those are the ones. Oh, what about if it says daily? Yeah. Now, some people may argue, well, what if it's a leap year? Then it's 366. Okay, we're just going to say, we're just all going to agree that we're going to use 365 anytime it says daily. We're not going to have to get out and be like, well, what year is this problem happening in? Was it a leap year? I don't think that matters. All right, so $1,500 is in an account compounded weekly. All right, so here's my magic keywords here. Compounded weekly means that my N is going to be 52 at 2.3%. So R is going to be 2.3 divided by 100. So 0.023. Move that decimal 2 places. How much money will be in the account after 5 years? Okay. So my final amount will be 1,500 times 1 plus 0.023 divided by 52, all to the power of 52 times 5. here's what I need you to do in your homework and even on the quiz. Uh-oh. This right here is your work. You showing me that equation is your work. Everything you do after this can be done in your calculator and you get an answer. Now, could human error happen and you push the wrong button and you get a wrong answer? Absolutely. I realize that that can happen. Our fingernails can touch the wrong button by accident. So if your equation is correct, if you write out this equation with all the right numbers in all the right places, and somehow your answer comes out wrong, I will probably give you majority of the credit for this problem because you showed me that this was the correct way to do it. And so probably it was just button error. All right, so make sure you write this down as a part of your work. I do want to show you on the calculator, if you have one of the newer ones, you can actually put in this fraction like this. So I want to remind you where that is. All right, so we had 1,500 parentheses 1 plus. So if I want to put in a fraction right now, which makes this problem significantly easier, this is under F1. Okay, so it's right here on the y equals button, but the F1 is green, so I've got to hit alpha, y equals, and that's where I get all my fractions. So I can choose option 1 there, and I get a nice fraction that I can put in. So that was 0.023 divided by 52. Then you can end your parenthesis, put in the exponent, 52 times, ooh, was it 5? Yeah. 5 years. So we end up getting 1682.77. So this equaled 1682.77, and I'm going to put that up here. This was alpha, the alpha button, and then the y equals button allows you to get that fraction. So if we change it slightly and the 1,500 is now the value of the car and it's depreciating monthly, how much will be in the account after 36 months? Okay, so what's going to change in our equation? We're going to have a negative sign. Good, because of the depreciating. This didn't change, so this would still be 0.023. What about this right here? What's t going to be? It's not going to be 36. T, well, is how many years? 3. Okay. I'm guessing you can set this up and plug it into your calculator without me guiding you through that. But just make sure that you always have your time in years. Yes, ma'am.
If it says monthly, is it not going to be 12?
Oh, you're right. I'm missing a piece. This would be N would be 12. Thank you. Yeah. N would be 12. T is 3. R is 0 to 3. And the depreciating means to subtract in the formula. All right, so if we change it slightly, 1,500 is now in an account compounding daily, same percent. How much would be in the account after 6 months? So let's see here. Compounding daily means that N will be 365. And if it says after 6 months, T would be 0.5. All right, and I think that this is fine. I just want to make sure that you know what to look for in the word problems. I think plugging it in ends up being pretty straightforward. Last equation that you need to know about, and just so you know, we will give you these equations, okay? So you do not need to memorize these equations. We will give them to you, but you have to know what the letters are. You have to know what the N stands for, what the T stands for, and that sort of thing. Our last equation is probably the one that gets used the most. It gets used because continuous compounding is really what happens the most. In the banks, it's always continuous compounding. If we are talking about organic substances that are growing or decaying, that's happening continuously. You know, a petri dish of bacteria isn't growing only when the lights are on, right? Okay, it's growing all the time, consistently. Your hair is growing all the time, consistently. So really, this is the most valuable equation to come across. The key words that you need to look for is if it says continuous compounding. Anytime it says continuous, this is going to be your key phrase. If it says that combination of words, that means use this equation. This equation is often called the PERT equation. So if you're talking to another teacher or another student or something and you hear, oh, use the PERT equation for that. This is that equation, because look, P-E-R-T, PERT. So it does have base E. So you can see right here, there's our base E. And so that's kind of what we learned yesterday, was that Bernoulli saw that as we started doing this more and more frequently, it approached a value of 2.718. So its growth factor was 2.718 when it was happening all the time. So when you use this equation, you can actually use base E and have it be growth or decay. It can decay continuously. How you will differentiate between those is with your exponent. So a growth equation would be A equals PE to the positive R times T. And the decay equation would just be A equals PE to the negative R to the T. As I said before, the rate will never be communicated as a negative rate. You have to know from the other wording in the problem that it is decaying, and you have to put in the negative. Okay. So let's take the same concept, the same $1,500 in an account that pays 2.3 annual interest compounded continuously. Find the amount in the account after 5 years. Now, before I do this, do you think it's going to be more or less than when we did it weekly? Well, let's find out. So, A is 1,500 as our original amount. Base E, R is going to be 0.023. This is growing, so it's positive, 0.23 multiplied times 5 years. And here was our previous calculation when we did it weekly. I'm going to do the 1,500. Remember, the E is over here on the ln, or it's on the divide sign. E to the 0.023 times 5. And it's more. Not a lot more, but it is more. So 1682.81. So it doesn't seem to make a humongous difference if it's $1,500, but what if it's $15 million? Then those cents become thousands of dollars, and that's a big difference. All right. Lastly, this is sort of a biological related problem. The population can be modeled by this equation. Notice base E, because it's biological. Right? Births don't just happen at like 6 a.m. once a day, every day, you know, so they happen all the time. In a problem like this, you'll usually have some sort of wording where it says like T is the number of years after 1990 and negative T is the number of years before 1990. You know, so there might be some sort of setup like that that you should pay attention to. So if it says find the population in 2005, what will be the T value? 15. Great. Okay. I'm going to spare us the plugging it into the calculator part because I think you could probably do that yourself. So then what if, let me put this here. What if the t-value, what if, excuse me, it was asking for the population in 1980? What would you use? The t would be -10, because that was 10 years ago. And then lastly, this last problem is kind of like what I was talking about at the beginning, where you need to use your graphing calculator, because notice what it's asking for. It's saying, determine when, so that's in what year, determine when the population will double. So right now, the population is 250,000. So what will be the population when it doubles? 500,000? Okay, so if we were going to set up this equation, it would look like this. 500,000 equals 250,000 e to the 0.01t. And look at where your variable is. It's in the exponent. Let me make this a little bit bigger. So now, your job is to solve this equation, but your variable's in the exponent. You can't subtract it out of the exponent. You can't divide it out of the exponent. You can't radical it out of the exponent. So this is where you need to use your graphing calculator. Now, these are ginormous numbers. That's going to make your window be crazy. Could we maybe reduce these two sides? Like, let's make this easier for ourselves. What could we reduce both sides by? How about, I mean, we could certainly reduce it by 1,000, and then 1,000 again, and then 1,000 again. How about 250,000? So think about that when you're doing these problems. See if you can kind of make the numbers a little bit easier. It will make your job in the window settings a little bit easier. So this works out to be 2 equals e to the 0.01t, and then you can put that t as an x when you put it in. So then, put this in as y1, put this in as y2, and find where they intersect. Where they intersect. Okay, so that does come up on your homework. Before spring break, we will learn how to solve this exact problem using logarithms. Right now, it's perfectly fine using the intersect feature. All right.